So first of all, what is a point of inflection? A point of inflection is where something changes from here, it's concave down, here it's concave up. And the point where it changes from concave down to concave up, or vice versa, we call a point of inflection. So how do we find these points? Well, you could find out that the derivative at that point is 0, and, oh, this is just an inflection point. A stationary point of inflection is where the tangent as well, here's my point, my tangent would be 0, that makes it a stationary point, and it's still changing from concave down to concave up. So an inflection point is just where something changes concave down to concave up. A stationary point of inflection is where the derivative is also flat. So this happens on x cubed graphs. Like the shape of that black graph here is your standard, could be exactly x cubed. We have inflection points when you have like an x cubed plus x squared plus x with more hills and more valleys. But when it's just a perfect x cubed graph, you will have a stationary point of inflection. So what we notice is that, first of all, the derivative is equal to 0. And secondly, that if you looked at tangents before and after, they don't change sign. Normally when you have an inflection point, a stationary point, you normally have a maximum or a minimum. And your graph changes from increasing to decreasing at a maximum, or changes from decreasing to increasing for a minimum. But we notice here that the tangents are both positive. On an x cubed graph, it's always increasing, even though there's a tangent of 0 in between. So on your number line, this is what you're doing. You take your derivative, right? Remember, we take our derivative, we put all our critical points on our number line, wherever the derivative is equal to 0. And this time you've been like, oh, this is weird, that it just kept going up. What does that mean? Well, it flattened out at x1. So we have a stationary point, but it's not a maximum or minimum because the graph has kept increasing during that time. Those are stationary points of inflection. The top one is a non-stationary point of inflection. Often we just call it an inflection point. It's when the derivative at that point is not 0, but the second derivative is. So if your first derivative is not 0, but your second derivative is, then you're going to have an inflection point. The gradient of the curve on either side has the same. So if we looked and picked a tangent here and a tangent here, you can see that the slopes would be both negative on either side of your inflection point. If one changes from negative to positive on either side, then you have a minimum, and it would not be an inflection point. Again, sort of the rule of thumb, if you want to show something in calculus, you need to show two things. If I want to show something's a point of inflection, the number one thing will be that the second derivative equals 0, but that is not enough to make something an inflection point. So for example, if you had x to the 4, there's my derivative. There's my second derivative. Obviously, if I set my second derivative equal to 0, I get x is equal to 0. And it appears that, oh, maybe that's an inflection point. But when we look at this graph already, okay, First of all, notice that if you set your first derivative equal to 0, you would also get x equals 0. And what we're going to do with the first derivative and the second derivative is that same number line. So on my first derivative, and this is why I like to label it, I plug 0. And when you plug something into your first derivative before 0, like a negative number, you will get a negative telling us that our function is decreasing. And then after 0, I plug something into my derivative, I will get a positive value. So this, I could use my first derivative test and look at this and say, I have a minimum at 0. If you take out your graphing calculator and you graph x to the 4, it looks very much like an x squared graph, just a little bit wider at the bottom. Oh, there's very little. I wasn't sure. So we have a minimum. If you take this same thing and plug in 0 into your second derivative, you will notice because it's an x squared, whatever I plug in will be positive. It's concave up on both sides. So 0 is not an inflection point because it didn't change from concave up to concave down or vice versa. So just showing that the second derivative equals 0 is not enough for an inflection point. Inflection points, it will always be 0, but we have to have another piece of information that shows it. So we can choose a couple of things. One, if we do our number line like this, and we show that before it's concave up and after concave down, perfect, you have an inflection point. Or if you go above and you find out that the first derivative isn't equal to 0 at that point, then you will also have an inflection. So this question tells us the first derivative is x minus 3 cubed. Now technically this is a chain rule because we have an x minus 3 inside of the x cubed. But when you do the chain rule, the derivative of the inside function is just 1. So technically it's a chain rule which didn't have any effect. F prime of 3 would mean plugging in 3 into the original equation. It's equal to 0. F double prime of 3, plugging 3 into our second equation, is also 0. And so the point P on the graph of F has an x-coordinate of 3. Explain why P is not a point of inflection. So we could say that in our first derivative, at 3, it's equal to 0. When you plug in something less than 3, like 0, you get negative 3 cubed, which is negative 27. It's going down. And if I plug in something after 3 into my equation, I get a positive value. So you could explain it's not a point of inflection because it's a minimum point. You could explain that the first derivative changes from negative to positive at 3, means the function is changing from decreasing to increasing. An inflection point will always either stay increasing or stay decreasing at that point. will see some North American books spelling inflection with a CT and British books spelling it with an X. So feel free to introduce a K. I'm going to have a new spelling. So what we're going to do now is we are going to sort of set up the pattern for all graphing that we're going to do with calculus. When we graph something in calculus, we are going to find all the maximum and minimum values we can. If we can easily find intercepts, we'll label them. Sometimes we won't be able to find them easily. And we are going to label all inflection points. So as a starting point, you might find intercepts if you can find them easily. A y-intercept, really easy. That one, plug in 0 for x, get 0,4. Does this one factor nice? No. So we're going to leave the x-intercepts. We could still use a quadratic formula to find our x-intercepts, but if this was a question on an exam where they wanted you to label x-intercepts, they'd probably let you use your calculator. And if you can use your calculator, then you should graph the whole thing on your calculator. Find maximums, minimums, intercepts, everything from your calculator because it's faster. So your exam is a little tight for time, and you're not given extra time. So anytime we can do something faster, we will. Now, our steps for graphing any graph is, with calculus, is after we find our intercepts, if we can, we will find our first derivative. So f prime of x is 6x minus 5. And you will find the critical points by setting it equal to 0. And so we get 5/6 as the only point that is a critical point. Make our number line, and now we can determine where something is increasing or decreasing. In this case, if I plug in something less, like 0, I get a negative number, meaning that it's decreasing. And then plug in something bigger than 5/6, like 2, that'll give me a positive value. That'll be increasing. And so we will get that 5/6 comma something is going to be a local minimum. We already know it's a minimum from our first derivative. This is the first derivative test. First derivative test tells us the two things that we find from our first derivative test is it's equal to 0 at 5/6, and it changed from decreasing to increasing to make it a minimum. The diagram itself just yells at you, by the way, it's a minimum, right? Because it's so obvious from the red to the green that the only way you could go down and then up is if you hit a minimum in between. Now, to find the y-coordinate of this minimum, we're going to need to type this into our calculator. So 3 times 5/6 squared minus 5 times 25/6 plus 4. Keep it as a fraction. I get 23/12. Plugging that into my calculator. So where do we find the purple value from? We found the purple value anytime we're looking for a point on our graph. We're going back to the original equation, because the original equation is the equation for all points. The derivative just tells us increasing, decreasing. The original one tells us any points we want. There we have our local minimum. After finding our local minimum, we find our second derivative. In this case, it's equal to 6. Take your first derivative, find the derivative of it. Normally, we would set our second derivative equal to 0 and solve. How are we doing? 0 equals 6. Okay, I hope you can recognize this is not possible. There's no solution to this. As hard as you can try, 0 is not equal to 6. So when we go to draw our second derivative line, normally we would put where our second derivative is equal to 0. In this case, it's not. It would be a complete blank line. You can plug any number you would like in. We could pick 75. Plug in 75. What's it equal to? 6. You could even like, oh, want to see my impressive math skills? I'll plug in pi. 6. Right? It's always equal to 6, which is always positive, meaning this is always concave up. And now you knew this already because it was a parabola, right? You know some things about parabolas. You know that they're always concave up. Right? The smiley face is like a parabola to begin with. And so we didn't need to do all of this work, but what we can now do is we can go on here. 1, 2, 3, and 23 over 12. 1, 2, 3. We can label our vertex, our local minimum, to be at 5, 6, 23 over 12. And we know that our graph is going up. Right? Because we know a parabola looks like this, but can you see that the first derivative is telling us, oh, it needed to be decreasing and then increasing. And our second derivative is telling us that it always should be concave up. But we knew this already because it was a parabola. Of course, in graphs that we're not as good at, this is going to be a really nice system. Oh, and I guess I can label not to scale. Should have thought of this a little bit. Everybody knows somewhere between 2 and 3 is the number 4. So we'll just pretend that little mistake. I probably should have labeled. Had I labeled 4 to begin with, I would have found out, oh, my parabola was actually narrower than I drew it originally. Okay, so. This does look like one that wouldn't be as enjoyable to graph anyway. First of all, can you see that your y-intercept, if you plug in 0 for x, is 0? Does this look like it will factor nicely? No, not really. Sorry, I'm playing around with factoring. We won't factor. But now we can find our derivative. Bring the 3 out in front. Set it equal to 0. I'm going to factor out the 2 right away. -2. And now, since it's an equation, I can factor out that -2. Can you see that you could have also divided both sides by -2? So either way, you either have the -2 out in front, it would be perfectly fine if you just had this. That would be the same thing. The second one is me dividing everything by -2. Since it's an equation, I can do that. The first one is me factoring. okay? If it was an x, I'd have to be careful. I wouldn't be able to just divide everything by x, because then I would miss some of my solutions. So I generally think factoring is a better strategy. But if you understand that when it's a number, I could have just divided both sides by that, perfectly fine. This does factor nicely. To x plus 5x minus 1. And so on our number line, we would have minus 5, and we'd have plus 1. Those are critical values. When I plug things into this, I notice that when I plug in something less than minus 5, negative 6, this factor would be negative, as would this factor, and negative times a negative would be positive. My graph is increasing. Then plugging in 0. 0 is really nice because you might actually want to use the original equation. Okay? Or either way, what happened here? When I use the original equation, I get positive 10. When I use this equation, I get negative 10. I'm feeling like something has gone awry, because it shouldn't be different depending on the equation. Or should I have, you know what? For figuring out this is my factored form when I made it equal to 0. Okay, I'm going to keep the negative 2 here. Because when I'm plugging things in, I need to plug into the original equation. By setting it equal to 0 and dividing out that negative 2, I changed my equation from the original one by dividing by that negative 2. So in reality, factored form is better, because now I have a negative times a negative times a negative. This would be negative in this section. So in solutions, finding the negative 5 and the 1, that negative 2 wouldn't matter. But in finding where f prime of x is positive and negative, I need to consider the entire thing, which included the negative 2. So I'm going to keep that negative 2 in the factored form, because I like using my factored form to figure out positive and negative. I find that mental math goes a lot quicker. So there's going to be a negative 2 out in front, which is always negative. When I plug in negative 6, this is negative, plus the negative out front will always be negative. Now, when I plug in 0, this one is positive, this one's still negative, the negative 2 out front is still negative, which will change this section to positive, to increase. And finally, plugging in something bigger than 1, like 2, this one's positive, the negative 2 is still negative, decreasing after that. So what do I know? I know negative 5 comma something is a local max or a local min. And I know that 1 comma something is a local max. And my number line with my derivative really shows me that. In order to find out the value that goes with negative 5, I have to go back to my original equation, plug in negative 5, so when I plug in negative 5, I got negative 66.67 to 36, negative 66.7. That would be an approximation. If you wanted to, you could have written it as negative 200 over 3. Then it's an exact value. Same thing when I plug in 1. This is going to be a little bit easier. Negative 2/3 minus 4 plus 10 I could write 5.33. Everybody knows how to quickly change a decimal to a fraction on their calculator? Using the fraction button under math. So I could write it as 16 over 3 or 5.33. So there's our first derivative. Now, inflection points, we find our second derivative. So our second derivative will be negative 4x minus 8. We can set this equal to 0 and solve. And we're going to get minus 2. Plugging in 0 into your second derivative using negative, meaning that it's concave down. Plugging in something less than negative 2, like negative 5, would give me a positive number. So negative 2, comma something is an inflection point. Okay, the easiest way to say something is an inflection point is to say the second derivative is 0 and it changes concavity. The harder way to say something is an inflection point is that the second derivative is 0 and the first derivative at negative 2 stays increasing. But I don't find that as intuitive as actually looking at your second derivative number line thing is really intuitive to see that it changed concavity and it was equal to 0 at that point. Okay? Now, to find out what exactly our inflection point is, I'm going to take out my purple pen because I would have to plug that negative 2 back into my original equation. Negative 2/3 times negative 2 or positive 2? Negative 2. I got negative 30.7, which as a fraction would be negative 92 over 3. So we find our first derivative. The first derivative test tells us if they're maxes or mins. We find our second derivative. Our second derivative finds our inflection point. We then go to our graph and we label everything nicely to scale. So I'm going to need to go down to negative 67. I'm going to need to go all the way to negative 5. I'm going to plot these points. So I've got negative 5, negative 66.7. I've got 1, 5.33. And I have got negative 2, negative 30.7. Now going to graph this, I actually like, and we know our x-intercept to be at 0 and our y-intercept to be at 0. So we know that it's decreasing. This is going to be a minimum, right? We know that it's got to curve down at that point as a minimum. We know that it's got to curve up at this point as a maximum. And it's going to change concavity. So I actually like starting from my inflection point and drawing that part all concave up, this part all concave down, and we've got our graph. The points that we could not find easily mathematically, we could not find those x-intercepts. But there's where we'll stop for today.